Hey Team Electronics and Coding, welcome to your screencast on buttons, a little bit of a review and talking about why we wire buttons the way that we do and how they work. Okay, so you know from an activity we did last week that buttons have 4 pins. If this is pin 1A, this would be pin 1B, and this is pin 2A and 2B. Now 1A is always connected to 1B. There's actually, like, these two are electrically connected always. It's kind of like there's a wire in between the two of them. There's actually a little piece of metal here. And 2A is always connected to 2B as well when the button is unpressed. However, when you press the button, you physically connect all 4 pins one to another. This is actually because there's a little disc of metal that when you push the button down, it makes contact in between all 4 pins. Some of you drew it like this in your activity, and some of you drew it with diagonals. All of these are kind of correct ways of thinking about it. Just know that all the pins are electrically connected when the button is pressed. Okay, now zooming down here to a little bit of code that we have seen, not exactly, but essentially we've seen this before. You all know that here at the very start of the program, we create a variable called button state, and we initially set that variable equal to 0. In the setup, and this button state is going to be a place where we store the reading of our button. In the setup, we declare our pins either inputs or outputs, and we do this because we're telling our Arduino what we're connecting to them. We know, or Arduino now knows that attached to pin 3, we have a sensor. So this means we're going to be reading it. And attached to pin 4, we have an actuator. And the sensor is, of course, our button. And we have an actuator, which is our LED, and we're going to be writing to it. Okay, so in the first part of our code, the first thing that we do is we store the digital reading of pin 3 in this variable button state. We set it equal, button state equal to the digital reading on pin 3. Because we're performing a digital read, we know that this reading can give us one of 2 states, right? A digital something is going to have 2 states. Either a reading of 5 volts, which is going to be a reading of high, or 1, or 0 volts, which will give us a reading of low, or 0. Okay, so let's actually talk about how the button accomplishes this. Well, the way we've wired it is on this side of the button, we've connected it to our power, our 5 volts. So because these 2 pins are electrically connected, if we were to take out a voltmeter and we were to measure the voltage at any of these pins, we would see that there's 5 volts. And anything in row 6, because we've connected it to the power rail. Okay, now on this side of the button, this is a different story. This part of the button is electrically connected to one another, but it's connected to the ground. So on this side, there is a reading when the button is unpressed. A reading on this side will be 0 volts. So this will be 0 volts. However, when the button is pressed, this side will toggle from 0 volts to 5 volts because now there'll be a connection across the button like so. And so the reading will change from 0 to 5 when the button is pressed. Okay, so the majority of the screencast is going to be talking about why we need a resistor on this side of our design. And because when we have no resistor, this is bad. And we're going to be talking about why. Okay, so here are two sketches. One, there's no resistor at all and no connection on, well, just a missing resistor. And here we replace the resistor with a wire. And we're going to be talking about why both of these are bad. Okay, so we said before that when the button is pressed, we'll get a reading of 5 volts on this wire, which is true even in this scenario. If we press the button, now there'll be a 5 volt reading on this side of the button, and which wasn't there before. But when the button is unpressed, in this sketch with nothing connection to the ground, we get what's called a floating pin. What this means is that the pin is not physically connected. I'm going to move this. So when the button pressed, this will work. It'll equal 5 volts, but when the button is unpressed, we get a float state. The pin is not physically connected to 5 volts or ground. Gonna move this. So you can see here, when the button is pressed, it'll be connected to 5 volts, this pin. But when it's not pressed, it's not connected to anything. It's floating. And this means that electrical noise in the circuit is going to cause readings that bounce back between readings will bounce between low and high, like randomly. It won't actually be random. There'll be a reason for it, but the reason will not be because the button is pressed or unpressed. So when the button is unpressed, other electrical components in the circuit are going to cause perturbations that are going to be read by this pin. And so even if you don't press the button, the light is going to flick on and off, because it's not connected to 5 volts or ground when it's unpressed. It's floating. So in order to correct this, we attach what's called a pull-down resistor, which is what's in this sketch right here. So it means that even when the button is not pressed, it won't be in a float state. It will be connected physically to the ground. Okay, so our other option, so not connecting this side to the ground is bad, right? We need to connect this side to the ground. But why do we need to do it with a resistor? Why can't we do it with a wire, like in this sketch? So here, when the button is unpressed, now we've connected it to ground, and we'll get a reading of 0 volts, which is great. We no longer have a float state when the button is unpressed. However, we've created a situation when the button is pressed. We've created a short circuit. And a short circuit is also just as bad, if not worse, than a float state. So you know Ohm's law. If not by name, then by description from last screencast, or 2 screencasts ago, which is voltage equals current, which is actually not a C, it's an I, times resistance R. V equals I times R. So in this situation, when we hook up a button directly between the 5 volts and ground, as soon as we press the button, we create a complete circuit that electrons can travel through from this side of the button to this side of the button and back to our Arduino. And in this situation, we've created a setup where the resistance of our circuit is extremely low. If we have a 5-volt system, this means that our current will be extremely high. So when the resistance of the circuit approaches 0, which it would in this case because we have no resistors, the current approaches infinity. So the resistance actually isn't 0, it's above 0, but our current gets really huge. So we have a huge amount of electricity moving from the power to the ground, power to the ground, power to the ground. And this is going to cause our circuit to heat up immensely. And it can even destroy our Arduino if we have too much current going through. Okay, so this is why we cannot just directly connect our button to the ground with a wire, is because we'll create a short circuit when we press it. Okay, so this is how you must wire a button. You have to connect it to 5 volts on one side and then ground on the other side with a resistor. In our cases, we are going to be using anywhere between 1 kilo ohm to 10 kilo ohm resistors as the resistors that connect our buttons to the ground. Okay, that's all.